Hello students, this is Usha from G.K.Jain High Secondary School. Today we are going to see Electricity Part 4 in 12th Standard Physics. In this we are going to learn about the application of Kirchhoff's law. That is nothing but your Wheatstone bridge. Let us move on to the topic. Current Electricity Part 4. Wheatstone bridge. An important application of Kirchhoff's rule is the Wheatstone bridge. It is used to compare resistance and also help in determining the unknown resistance in electrical network. The diagram shown over here. The bridge consists of four resistors P, Q, R and S. Connected you can see there. A galvanometer G is connected between the point B and D. The battery is connected between the point A and C, and current through the galvanometer is Ig and its resistance is G. Now we are going to apply the Kirchhoff's current rule to the junction B. So we get I1 minus Ig minus I3 equal to 0. Apply Kirchhoff's current rule to the junction D. I2 plus Ig minus I4 equal to 0. Apply Kirchhoff's voltage rule to the loop ABDA. I1P plus IgG minus I2R is equal to 0. Apply Kirchhoff's voltage rule to the loop ABCDA. We get I1P plus I3Q minus I4S minus I2R is equal to 0. When the point B and D are at the same potential, the bridge is said to be balanced. As there is no potential difference between B and D, no current flow through the galvanometer. That is, Ig is equal to 0. Substituting Ig equal to 0 in the above equations, we get I1 is equal to I3, I2 is equal to I4, and I1P is equal to I2R. Substituting all these values in the fourth equation, we get I1P plus I1Q minus I2S minus I2R is equal to 0. So taking the like terms, I1 into P plus Q is equal to I2 into R plus S. Now dividing the equations, we'll get P plus Q divided by P is equal to R plus S divided by R. Making into separate terms, 1 plus Q by P is equal to 1 plus S by R. Cancelling 1 on both the sides, you will get Q by P is equal to S by R. Inverting, will get P by Q is equal to R by S. This is a bridge balance condition. Only under this condition, the galvanometer shows null deflection. Suppose we know the value of two adjacent resistors, the other two resistors can be compared. If three of the resistors are known, the value of the unknown resistance can be determined. Next, we will go into the meter bridge. Here the diagram shown over here. The meter bridge is another form of Wheatstone bridge. It consists of a uniform manganese wire AB of 1 meter length. The wire is stitched in a meter scale on a wound wooden board between two copper strips C and D. Between the two copper strips, another copper strip E is mounted to enclose gap between G1 and G2. A known resistance P is connected in G1 and the unknown resistance P is connected in G1 and a standard resistance Q is connected in G2. A jockey is connected to the terminal E on the central copper strip to a galvanometer, high distance, and your jockey is connected. The exact position of jockey on the wire can be read on the scale. So a Lagrange cell and a key are connected across the ends of the bridge wire. The position of the jockey on the wire is adjusted so that the galvanometer shows zero deflection. Let the point be J. The length AJ and JB of the bridge wire now replace the resistance R and S of the Wheatstone bridge. Then P by Q is equal to R by S is equal to R dash AJ divided by R dash JB. We have P by Q is equal to AJ divided by JB, which is equal to L1 by L2, where R dash is the resistance per unit length of the wire, so they cancel each other. We have P is equal to Q into L1 by L2. The bridge wire is soldered at the end of the copper strip. So, due to imperfect contact, some resistance might be introduced at the contact. This is called as end resistance. The error can be eliminated if another set of readings are taken and with P and Q interchange and the average value of P is found. Then we are able to find out the specific resistance of the material of the wire in the coil P. The radius R and the length of the wire are measured. The specific resistance or resistivity rho can be calculated using the relation resistance R is equal to rho into L by A. By rearranging, we'll get rho is equal to resistance into A by L. If P is unknown resistance, then we have rho is equal to P into pi R square divided by L. Next is potentiometer. Potentiometer is used for the accurate measurement of potential differences, current and resistance. It is 10-meter long wire, uniform wire of manganese in parallel rows, each of 1 meter length on a wooden board. The two ends A and B are brought to the same side and fixed to copper strip with the binding screws. A meter scale is fixed parallel to the wire. A jockey is provided for making contact. A steady current is maintained across the wire CD by a battery. The battery key and the potentiometer wire are connected in series from the primary circuit. The positive terminal of the primary cell of EMF sigma Xi is connected to the point C, and the negative terminal is connected to the jockey through a galvanometer and a high resistance. This forms the secondary circuit. Now, let me keep the jockey and make contact on the wire. If the potential difference across Cj is equal to the EMF of the cell Xi, then no current will flow through the galvanometer and it will show zero deflection. Cj is the balancing length L. The potential difference across Cj is equal to IRL, where I is the current flowing through the wire and R is the resistance per unit length of the wire. Hence, Xi is equal to IRL. Hence, I and R are constant. Xi is directly proportional to L. The EMF of the cell is directly proportional to the balancing length. Next is comparison of EMF of two cells with a potentiometer. To compare the EMF of two cells, the circuit connections are made. It is shown in the diagram. Potential wire CD is connected to a battery key in series. This is called as your primary circuit, which already we have seen in the before case also. The NC of the wire is connected to the terminal M of a DP-DT switch, and the other terminal N is connected to the jockey through a galvanometer and a high resistance R. DP-DT switch is nothing but double pole double throw switch. The cell whose EMF Xi1 and Xi2 to be compared are connected to the terminal M1N1 and M2N2 of the DP-DT switch. The positive terminal of the battery E1 and epsilon 1 and epsilon 2 should be connected to the same end C. The DP-DT switch is pressed towards M1 N1 so that cell Xi1 is included in the secondary circuit, and the balancing length L1 is found by adjusting the jockey for zero deflection. Then the second cell Xi2 is included in the circuit and the balancing length L2 is determined. Let R be the resistance per unit length of the potentiometer wire and I be the current flowing through the wire. We have Xi1 is equal to IRL1 and Xi2 is equal to IRL2. By dividing them, we'll get Xi1 by Xi2 is equal to L1 by L2. By including a rheostat in the primary circuit, the experiment can be repeated several times by changing the current flowing through it. Next is measurement of internal resistance of the cell by potentiometer. To measure the internal resistance of a cell, the circuit connections are made as shown in the diagram. The NC of the potentiometer is connected to the positive terminal of the battery BT and the negative terminal of the battery is connected to the end D through your key. This forms the primary circuit. The positive terminal of the cell Xi, whose internal resistance to be calculated is determined, is connected to the NC of the wire. The negative terminal of the cell Xi is connected to the jockey through a galvanometer and a high resistance. A resistance box R and key K2 are connected across the cell Xi. With the K2 open, the balancing point J is obtained and the balancing length Cj is equal to L1 is measured. Since the cell is in open circuit, its EMF is Xi is directly proportional to L1. A suitable resistance included in the resistance box and key K2 is closed. Let R be the internal resistance of the cell. The current passing through the coil and the resistance R is given by I is equal to Xi divided by R plus R. The potential difference across R is V is equal to Xi R divided by R plus R. When the potential difference is balanced on the potentiometer wire, let L2 be the balancing length. Then Xi R divided by R plus R is directly proportional to L2. R plus R divided by R is equal to L1 by L2. 1 plus R divided by R is equal to L1 divided by L2. And rearranging will get R is equal to R into L1 by L2 minus 1. Therefore, R is equal to R into L1 minus L2 divided by L2. Substituting the value of capital R, because we know that value L1 and L2, the internal resistance of the cell is determined. It can be repeated with different values of R. It is found that the internal resistance of the cell is not constant, but increasing with increase of external resistance connected across its terminals. Yeah, you have now learnt about the Wheatstone bridge and know how to find out the unknown resistance. Thank you, students. We'll meet you in the next video.